Swayam Prabha. Digital India. Educated India.
So we are looking at basic concepts of static equilibrium. So what we have been saying is that we have a particle here, and on which we have a lot of forces acting on this one. Okay, and then have this is particle, and we have rigid body here, where we have a body here which has size and shape, and we have a system of collected bodies and combination of bodies. So which are interacting with each other. They are connected in some way or other, and there are many examples for that. And for example, we have, you see these kind of structures, roofs, right? So a roof, something like this. So this is a static structure, or might quite often we also have say this is a kind of pliers, so with some joint here, something going through this one, or we have a host of other examples also, something like we have loosely connected bodies, something like this, which are just touching each other. So all these things are going from a particle to one body to a number of bodies put together, and so they are all connected. So our final aim is to analyze these kind of structures. Why this is important is that your Newton's laws are enunciated only for a particle. Okay, so only for a particle. So our Newton's laws start from here only, saying that the very first law says that if a particle is acted upon by force and if the net force is 0, so then it will be in a state of rest or in a uniform velocity motion. So that's what's said here, and then we have to graduate from here to here to here, and this is the static part, and then we also have to do the same thing for dynamic. Okay, so here what we, many of these things of course you are quite familiar, but let's go ahead in a systematic manner, and it will also be a nice brush up. So here we know that since this is under equilibrium, that means that there is either is in the state of rest, we assume that it is a state of rest, and what we have here is that the summation of all the forces here is 0. So that's what this says. So this is a vectorial equation, and this vectorial equation can be in one dimension, it is only one equation, only in x direction. If it is two dimensions, it can be two scalar equations. And if it is in three dimensions, it is equivalent to three scalar equations. So in 3D, in space, so this is equivalent to three scalar equations. In the sense that you can write Fix is equal to 0, I going from 1 to n, and the other 2. So we can say that Fiy summation 0, Fiz summation is 0. So that means that we have three scalar equations, in the sense that in this particular problem, if you have a number of forces like this one, and maybe 5, 10, anything like that. So what essentially means is that, so if you have, since you have three scalar equations, it is possible to solve for three unknowns. You have, say, if you have 10 forces here, if you, out of which you know 7, the other 3 can be solved. Okay, for 3, if you know the directions, 3 magnitudes, or in some sense, sometimes you know that there is a force acting, so you can even find out the magnitude and sometimes the directions also. So essentially, it is 3 equations you can solve for 3, right? So like this, so we can go ahead. What are the issues here for a rigid body? So since all of them here acting on this thing, either you can write it in the vectorial form, or we can even write it in a form of polygon. So you can even write it in the form of a graphical sense. So in the sense that you can write F1 like this one, and F2 like this one, and F3 like this one. So graphically, we can even write like this one. I hope you can see that there's a F1 and add an F2 and an F3, F4. So they will all come back to the same origin. So that way it's a closed polygon. So whenever you have forces like that one, this is under the concept of equilibrium, right? If it is unclosed, so that means that if there is a net force, it will cause motion, that's acceleration. So then we come to this one. So there are, in the rigid body, we have some external forces acting on the body, and then, okay, so then how do we proceed? Because this set of equations are given only for a particle. Okay, so if you consider that this is, there are a number of particles here, obviously this is made of a number of particles here. So if this is under equilibrium, we take it that the whole rigid body as well as all the particles are under equilibrium. Each particle is under equilibrium. So we have some issues. I'll talk about that as we go on. Okay. So if you think that each particle is under equilibrium, there are n number of particles here. So we can make this equation for particle. Okay. So if you make the equation for each particle here, so what we have here is that, for example, there's an ith particle here. So this is an ith particle here. There may be some force acting on this one, some Fi. Let us put some superscript ext. So this is external force. Apart from this, so since we are isolating this particle from the rest of the other particles, so they are all molecules. So there are all kinds of electromagnetic forces, okay, attractions, repulsions, and so on. So we have, say there is a jth particle here, and there is Φj. So that means that there is a force acting on the highest particle because of jth particle. So like this, so you have a number of particles which are in the neighborhood. So where there is an Fij, Fik, or Fi1, Fi2, Fi3, where the first subscript denotes where they are acting, and the second subscript denotes where they are coming from. Okay, so like this, so we have the we have an external force which is from the external agency. So we know there are many kinds of forces. We don't go into all kinds of forces. So there are 4 types of forces. Let's not go into that. So there are forces because of contact. So if there are two bodies are in contact, we call them as contact forces, right? Or on the other hand, we also have forces which are generated by fields, by potential fields. Like if you have a gravitational field, so there are forces which are being acted upon by Earth, and then that force is acting on each and every particle. So that is a distributed force all over the body, and that is a body force. So these are the two forces which we take into account, either the contact forces or the forces because of the field, gravitation. Okay, or even any other magnetic field, any other. So only two forces which we consider. Okay, so if you take that, so now what we would like to do is that there will be n number of particles, there will be infinite number of equations, right? Every particle has a number of surrounding particles, and each particle is under equilibrium. So what we are assuming here is that, I'll come to this later. So can I apply this equilibrium equation for a particle for an ith particle? So if I do that, then summation of all the forces, an external force as well as these internal forces which are acting on this particle, should all be together equal to 0. So something like here. So that means that I will put Fi, I'll put Ext, saying that these are the external forces. Okay. And apart from this, so I have all these things. So you can say Fi1, Fi2, Fi3, and so on. So I'll put it as a summation here. Fij, j going from 1 to n, and this is a vector quantity. And so these are the external forces, and these are due to the internal forces because of the neighboring particle. So all these put together, I'm sorry, plus. So all these things put together should add up to 0, right? So then this is the equilibrium of ith particle. So I can make these equations for jth particle. Similarly, I can also do it for jth particle. So in which case, this is for the ith particle. And for jth particle, if I write it, then it would look like Fj external plus here Fj, say k here, and k going from 1 to n. So I can write down these equations for n number of particles, all the particles, and then if I add, what happens? If I add all these things, then on this side we have all the external forces, right? If I add it, so that means that these are all summation of all these external forces. And what happens to this one? So this I will write it as double summation I, j, and so what it will be? This is a double summation, right? So I have particles acting on the ith particle and forces acting on the jth particle, and so on and on. So if you look a little closely, what is Fij and Fji? If I add these two, there is an Fij coming here, and there is Fji coming on jth particle. So jth particle, there is an Fji due to I. The force on jth particle due to I. What happens if I take the summation of these? So these are equal.
0, sir.
0. Yeah, thank you. Thank you very much. Yeah, so this whole thing turns out to be 0, right? Because these occur in pairs and equal and opposite. Fij, Fji are equal and opposite and collinear, so that also turns out to be 0. So finally, what it will turn out to be? Good. So we have, so this whole term drops out and leaving only Fi external. Okay. So this is interesting for us. Yeah. So I will write it here again. My board is small. So that means that for this is a very interesting result. So that means that, so for a rigid body also, so all the external forces which are acting should sum up to 0. Okay. So this is because we are assuming that the body is at equilibrium. If each particle is under equilibrium, then the whole body is also under equilibrium. In fact, I have a question regarding that a little later. I'll put that question. So there is Fi here. Okay. So this is one equation. Actually, there are since we have a body here which has a size and shape compared to particle. Particle, we have just all the forces acting on that point. Whereas if you come to the rigid body, they are not acting at the same point. Okay, they are acting at different points. So what it will happen here is that we also now have to be bothered about moment. Okay, moment of this is one equation. We'll use it. Moment of a force. So this is very important because you take a body here, and if you have a force here, external force, so this will be say about the point A here, and it will exert a moment about a point A here. So how do we do that? One of these things is that this is a very simple one. So if you have drop a perpendicular D here, and then F, and F times D is the moment. So that is the magnitude, and also it has a sense, and sense using the right hand thumb rule. So in fact here this will be doing a clockwise moment, and probably. So what is the magnitude here? So the magnitude here is that the moment about A, the magnitude is D times F. So this is fine, but we can even generalize it, make it a little bit better by looking at some point B here, and let's call this. So we have we have taken a point B here on the line of force, and then now we call this as a vector AB as R. So we know that now this can be represented in a much compendious manner as MA is equal to R cross. So you can very well see that R cross F has a magnitude same as FD, as well as now we also have come across, we have made this into a vector. So the moment now is the magnitudes FD, as well as now it has a direction. So here we say that it's going into the board, but you can really generalize it to a 3 dimensions. And what we say here is that if you have another force here, maybe this is F1. So if you have another force in some other direction, so we can keep on doing it for n number of forces. So the beauty of this one is that we can treat moment also as a simple vector quantity, just like we have seen forces. So this moment we can add a number of forces. So say R1, F1, and R2, F2. Like this, we can add like this one. So that means that we have M1, M2, and so on. So the total moment is nothing but a vector addition of all these forces, right? So we can treat, just like we treat the force as a vector, we can also treat moments as a vector. There's one thing which we keep coming across is so this I said a number of forces like this one, and we can also have another thing, like if you have 2 forces. In fact, you know that there's a transmissibility. Of course, that's a very simple. So either you can assume that the force is acting here or force is acting here. So its effect on this body, it is simply a vector, right? Forces can be, the vectors can be transferred either here or here, it doesn't matter. And as well as the moment also will not change. So this is called a transmissibility, and the effect of this force, since this is being a rigid body, it doesn't matter whether you assume it here or assume it here, doesn't matter. Only when you come to the next higher level class, maybe deformable bodies, of course, the effect will be different whether it acts here or acts here. But as far as rigid body is concerned, we need not worry about those kind of things. There's also another thing which we keep coming across is a couple. So this is a little bit of confusion. This raises sometimes moment couple or simply couple. Okay. So this moment due to a couple of forces. Okay. So what we mean by, so if you have two forces equal and opposite like this one. So if you have two forces F1 and F2 equal and opposite, then it will constitute a couple. Okay. Equal and, so if they are equal and opposite. So what is its effect? This is very important for us to understand, is that the effect of this one is, now we are putting it as two forces which are separated by a distance d. So we know that the effect of this one is as a vector summation they come to 0. So they will simply equal to, so this you have done it number of times probably. So the moment here is simply f into distance d here, and so that means that it only depends upon the, so these two can be replaced by, so these two forces which are equal and opposite, parallel to each other and separated by distance d, can be simply replaced by a moment. Its effect is simply a moment, or sometimes we call it as a couple. Okay. So this is because we can even, you can even reduce the distance and have the same couple magnitude by increasing the force. So if you keep on reducing this d and keep on increasing f, what happens? So they will come closer and closer. So then what happens here, if you make it closer and closer, so what happens is that they collapse on each other, but they become infinite. The forces become infinite, the distance may be reducing, and but however the magnitude remains same. Okay. So when they reduce to this one, so then they can be replaced by a simple couple. So the effect of these two forces which are equal and opposite and parallel is simply equivalent to an F into D. So it will not enter the force equation. Okay. It will enter the moment equation directly because there is no force here, right? Now it is generated by two equal and opposite forces. So it is now finally equivalent to a moment. Okay. Either way. So what happens? Why is, because if you do this equation, if these two are equal, if you add them, you put them here, and if you add them vectorially, it will turn out to be 0. So obviously they will not enter this equation. But however, when we use a equation like this one, so that will enter a couple. Okay. So these are some of the things which you have to keep in mind. Now I'll ask you a question here, is which I was telling, is that for a rigid body under equilibrium, we derive this equation. What is the basis for this one? So the basis for this one is what? Basis for this one is because each particle in the system is under equilibrium. Each particle is under static equilibrium, and then we have derived, right? We have the external forces, we summed it up, and then we derived it, right? So now I ask you a reverse question. If sigma Fi is 0, all external forces if I add up to 0 on any body, does it mean that each particle is under equilibrium? Okay. Is somebody talking? Matthew, are you saying something? Not necessary. Good. Any answer for it? Of course, what you said is right. It's not necessary. So then how do we make it? Yes, it is. So under what conditions it will become? So if all the external forces add up to 0, torque need to be balanced. No, that's not right. Yeah. Torque, of course, will balance that. That's not a point right now we worry about. Okay. So I hope you have understood. So we have taken that each particle is under equilibrium, and then we said that all external forces should add up to 0. So let me just expand this question, because we need to consider rotation. Now, let me just consider a 1D. Okay, this is a very important thought provoking, right? Whenever one direction is true, it doesn't mean that the other direction is true. The sum of internal interactions of the rigid body is 0. It's not that clear, but let me explain. Okay, so this is true only for rigid. Okay, only for rigid body. It is not true for a body which is flexible, or maybe springy kind of structure, which is flexible, deformable, something. So let us look at this thing. A very simple 1D example. Just a 1D example. Okay. So let's assume that I have a particle here, and I have another particle here, 1 and 2. And let us say there's a force here, and let us say there's the force here, and these two are connected by a connection, maybe flexible, maybe rigid. A bomb exploding in vacuum has no external forces, but is not in equilibrium. Yes, that is the effect of it, but why? Question is why, and under what circumstances they each particle will be under equilibrium. So if you look at this one, this is a very simple, and F1 is acting and then F2 is acting like this one on two particles joined by something. Okay, and what is a joint? So that's what we worry about. And then what happens is that if, for example, if what my question is that if F1 plus this one dimension, okay, is equal to 0, does it mean that each particle is under equilibrium? Not necessarily. You can very clearly see that they are equal and opposite. Means that what? Let us see. So that means that there's a force acting here, and physically this is what it is. So if I have F here and then F here, so you can very clearly see that these two external forces add up to 0, right? F1 and F2, they add up to 0. But does it mean that the particles are not moving at all? You can very clearly see that they may go into some kind of vibration, right? Very clearly, or they may come and close to each other. The second part we used in the derivation should be able to 0 is the net force is 0. Okay. Good. So you are thinking, I'm quite happy that you are sending the messages. Good. So you can, this is quite obvious. Just because the two external forces are adding up to 0 doesn't mean very clearly that each particle is not under equilibrium. In fact, they keep moving if this is a flexible connection. This is a flexible connection. So what should be the force in this one so that the particles are also under equilibrium? Okay. So let's look at this one just quickly. It's not very difficult. Say I have an F12 on this one. I have 1 and here, and I'll apply it very simply. I'll use the dynamics equation. Just that is very, very simple. We'll come back to dynamics anyway later. And so this is, let's say, M1 and M2 here. So what is that I have? So I have F1 minus F12 is equal to M1 1, and here 2 plus 1 is equal to, in fact, I can even, since I'm showing the directions, I can simply replace it by smaller. Okay. So because this has to be equal. So whether it is a spring or a rigid connection, this is an internal force should be equal and opposite. So I'm using dynamic equation. Okay. From basic Newton's laws. I'm just going a dynamic equation. So if you look at this one, so what I have here is that I'm just putting it A1 and simply here so since what we know here is that since it is a rigid connection, if it is a rigid connection, then what happens if the connection is rigid, if the connection is rigid, then what happens? The A1 has to be equal to A2, right? The distances, that's what rigid body definition is. The distances between the particles will not change. If this is a one-dimensional motion, so if this is moving with a certain velocity or acceleration, this also should have the same velocity and acceleration. So if we put this one, I'm just trying to find out if the body is made of rigid, what should be the force? That's my goal. So if A1 is equal to A2, then what I have here, so I will replace this F12 and F21. They are the same magnitude by simply F. Okay, simply. Let me replace it by this one. So then I can calculate the, so what I would calculate here is I'll take this one onto the other side. Is equal to, so from this I can calculate what F would be. What will be F? So F will be, how much is that? So F I can calculate as, I'll calculate F1 M1 minus F2 M1 divided by M1 plus. Okay. So I just calculated what F would be. So I just multiplied by with M1 M2 and I got F1 M2 minus F2 M1 divided by M1 M. So what will be then? What will be F? What will be F? So since we are assuming, our premise is that it is, as a system, it is under equilibrium, which means that F1 and F2, F1 plus F2. So if F1 is what is it? If it is under equilibrium, as a system, then that means that F2 is equal to minus F1, right? F2 is equal to minus F1 because we took F1, F2 both in the same direction. So if it is under equilibrium, so this should be so. And then what happens here is that say 1 and I can add F. So which is simply F1. Understand? So that means that the internal force now is equal to F1. So if I write those things again here, so what is this force here? This acting is nothing but for F1, and on this one I have this F2 which is equal to F1 and this is equal to 1. Okay, so that means that under the assumption that we have rigid connection, so what I found, the internal force is simply equal to F1, right? So now can you see that this particle is under equilibrium? Okay, similarly here since F1 and F2 are equal magnitude, so this is also under equilibrium. So this is under equilibrium, as well as this is also under equilibrium. So what we are finally arrived at is that, so if you have a rigid body where the particles are connected by a rigid connection, so which means that in one dimension they will all be having the same acceleration. So if so, then if the external forces do balance, then internal forces will be such that each particle will be under equilibrium. Okay? So this is so that means that if you, for a rigid body, if you make sure that the external forces do balance, then internal forces will be generated in such a manner that each particle will be under equilibrium. Okay, so this is, again I caution you, this is only true for rigid body. If the connection is made of say some flexible thing like that of a spring which is deformable, so this will not hold good. So that means that the rigid body will not be any more rigid, it becomes a flexible body, and then it's altogether a different field of study. It's a different field of study because we will create accelerations, we create vibrations, so on. So here for our mechanics course, so we restrain ourselves. Okay, we confine ourselves to a rigid body motion. Okay, so finally what we say here is that if external is 0, so this is still not complete, because I still have to consider some of the moment equation. So what if this is 0, then each particle will be under such that sigma Fi so the internal forces are such that each particle will be under equilibrium. So is that clear? So that means that it is not automatic that if rigid body is under equilibrium, that these equilibrium equation will hold good for each and every particle. So this is only true for rigid body. Okay, the internal forces will be such that each particle will also be under equilibrium. Okay, now let's move on to something more. Now let's talk about this is how many equations is this? So for a rigid body, so we have one. So what we have said is that this is one equation, right? I mean, maybe it's equivalent to 3 scalar equations, but this is one vector equation. Okay, so this is not enough. We need something more than this. Okay, so what are the other equations that make the, what is the problem with this one? Why this is not enough? In fact, somebody was saying something earlier. In fact, why this is not enough? Is this good enough for the body is under in a state of rest? Okay, we forget about uniform velocity. Does it imply that the body is under completely state of rest? No, it will not. What is the problem? What is the problem? Will it guarantee for us that the body is in a state of rest? Internal forces? No, it's not internal forces. It is something more than that. Let's look at a very simple case of which I just talked about a couple. If you have rigid body, I have two forces, equal and opposite. This is a couple, right? Moment couple. What is sigma Fi here? I have two external forces which are equal and opposite, and which is separated by a certain distance d. And what happens to this one? This is satisfied. But is it in a state of rest? What is the problem here? What is the problem? So this is equivalent to, you can see that this is equivalent to a moment. There is no Fi here, but all these two equal forces will boil down to a simple a couple. Moment is there. Yes, exactly. That's what I said. Exactly. So we have this equation is satisfied, obviously, right? This sigma Fi is 0 because these are the equivalent opposite. So they turned out to be a vector sum being 0. Uniform translation motion. No, just think still, it is not under equilibrium. There's something is happening. What is that that's happening here? Rotation, isn't it? So if you subject a body to this kind of moment, what's going to happen? It's going to rotate. Okay. So its translation is arrested by this equation, but rotation is not constrained, right? It is going to go under rotation. Okay, at the same place, but it's going to go under rotation. So this leads to rotation. So we haven't stopped the body from rotating, right? How do we do this? So what additional equations which we need so that we can stop the rotation? In fact, if you look at the basic degrees of freedom, okay, if you look at basic degrees of freedom for a two-dimensional motion, okay, so this is, let's assume that this is moving in a 2D. This is just a slab which is subjected to something like a table here. I have body, I apply all the forces in plane, and the body will undergo some motion. So here, if you look at a two-dimensional body, the body has 3 degrees of freedom. One is a translation in the x direction. A second, it can translate freely in the y direction, as well as what is the third motion? Third degree of motion is also a rotation. Okay, so you also have 3 degrees of freedom for this one, but this, how many equations will it give? It will give in 2D, it will give only 2 scalar equations. So we need one more. We need one more equation. So where will we get it from? Where will we get it from? Okay, so this I borrow something from which we are going to discuss later, the equations for dynamic motion. Okay, if you, I'll just, what is that? I'll borrow that and I will discuss that. Okay, what is that under dynamics? So kinetics, okay, dynamics of rigid body. I'll simply write it here. We will do later, maybe after a month or something. So what we have here is, this is based on our second law. So where we have, say, F external forces, say all external forces is equal to mass times acceleration. So sum of all the forces here, external forces, will create the mass times acceleration. So here I'll put, we need a subscript, because if you look at the body, so if the body is translating and rotating, which point are you talking about? Okay, so because this acceleration is per a point, the acceleration is per a point, and then I have to put a subscript here to which it refers to. So it refers to, well, we see these equations later. Please take it from me that we are going to derive all these equations. Okay, so the external forces summation as is equal to mass. There is also one more equation which we are going to do it later, is the moment of all the forces about G is equal to Ig times. So let's just do it for 2D. let me do it for 2D, which we can extend it later through 2D. So if I do it for 2D, so what I mean here is that the set of equations here are the sum of the external forces. So I also have a G here. So this creates an acceleration for G. So that means that it's going to create an acceleration here for G. So the effect of these forces, maybe I'll write. So the effect of this is, I have a G here. So the effect of all these external forces acting here, F1, F2, and so on, so will lead to a acceleration for the center of mass. Okay, you know center of mass. That's one part. Apart from that, so this also will create actually a rotation. It will also create a rotation, which was originally like this one, may also rotate. So that is what this equation is going to tell. So that means that the moments of all these forces about G will cause an angular acceleration alpha here, and of course instead of m we have here inertia. This is the inertia term about G. Okay, so in 2D obviously you have not only two equations, okay, sigma f is equal to mass times Ag. So we also have an additional equation to talk about the rotation. So this is angular acceleration, alpha is angular acceleration, right? And obviously this, if you integrate it, you will get angular velocity. If you integrate it, then you will get a rotation theta. Okay, so that means that this is going to tell us about the orientation of the body, whereas this is going to tell us about where the position G. Here you have Ag, you can integrate it to get velocity, you can integrate it to get the position. So that this is equivalent to three scalar equations. This is equivalent to two equations in 2D, and this is just one equation, and you have three equations. So thus we require three equations to tell where G is and to tell what is the angular position of the body. Okay, so the same thing we can apply to this. I will do it later. Okay, so if we want to apply it to statics, what is it which we have? And also, well, maybe I keep telling you. So this is because the body here in two dimensions has 3 degrees of freedom. One is translation x, translation y, and rotation. So this set of equations will tell you all about those three. Okay, three equations. So if you want to specialize it for statics, if you want to specialize it for statics, so what do? The right side terms will drop. So that means that we have Fi, all external forces will sum up to rho, as well as all moments about G also will add up to. So this is for 2D, we can even make it for 3D. So if it is in 3D, then we would say that this is a vector. Okay, and similarly this will become 3 equation. Okay, so this is the static equilibrium. So I borrowed these equations obviously from the analysis of dynamic case. Okay, mass times acceleration. So this is what we deal with now. We are going to, this is what we did. We said that all external forces should add up to 0, but here this equation also tells us that the moment of all the forces about G, okay, about G should be, okay. I think I'll stop here. I hope you have understood why we need equations, so many equations, and what is the significance of each equation. Okay, so we'll meet it. Thank you.